Nice! Oh, what? It's not working? Huh. Mine's appearing. Interesting. Keep an eye on it. No good. Hmm. Oh, okay, cool. It's working. Great. Great. All right. Let's get this show on the road. Oh no. Where's the screen? Gotta get the screen going. Nice. All right. I expect not everybody to come to class today, given current events. But luckily, the material is kind of just definitional right now, if that's a word. If I can make up words. We're in the sort of definitions part of the subject, and every subject starts off like that. If you remember in group theory, in the beginning, all we did was kind of play around in DN or AN or whatever. Here, let's have some fun. And then you learn general theorems and so on, slowly. So that's where we are. That's the kind of material we're looking at right now. And so students, or student, singular? Student, actually no one, because there's 2 viewers. That means it's me and algebraically challenged. So nobody. Maintain. Oh, RDL's here. Oh, so that's the 2. So RDL. Maintain and expand your list of examples. All right, so that's the kind of thing we have to do. Bulk up on examples of rings. Rings with which are integral domains, which are not, which are fields, which are not, etc. Oh, really? Wait, you already taught AC? Insane. There might be other reasons why the students aren't showing. Okay. And then, then I'll do a simple theorem. Then I'll say what the characteristic of a ring is. And then characteristics of integral domains. And then ring homomorphisms. That's the plan. That's the order of events that I hope to do. Okay, so just really quick about examples. You want to learn how to like quickly grow examples from known examples. Okay, so here's one way. Okay, you have two rings. One way. One method. Got two rings. You can create a new ring. It's called the product. This is a set of pairs. You know, the product set. And what's the multiplication? The add and multiply component-wise. Okay? Notice this ring has a 1 if both of the rings have a 1. The 1 is 1 sub 1 and 1 sub 2. It's bad notation, but you get it. All right? What's 0? 0, 0. And then you add and multiply and go have fun. Teacher's pet crow, welcome. Awesome. Okay. So that's the one cheap way of making a ring. By the way, whenever you do this, you're never gonna get an integral domain. This is very rarely do you get an integral domain. In fact, the only time you get one is if both the rings are the 0 ring. So that's just the wrong. I mean, it's 0 ring is hilarious ring. Okay? So very rarely do you get an integral domain, because if you do this, the multiplication of these two types of elements is 0, 0. So you got some 0 divisors. Tons of 0 divisors. Okay? Awesome. So you're not going to get nice rings this way. You're going to get interesting rings, weird ones. Okay, another method. If you have a ring already, then you get a new ring. You can get what's denoted R adjoin X. This is just the polynomial ring whose coefficients are in the ring R. Now, polynomial expressions with coefficients in the ring R and the variable is X. So let me write every element down. Where the number of terms is allowed to be any finite number. And how do you add? Oh, and the Ri's are in R, in the original starting ring. How do you add to? Collect like terms. Okay, add is collect like terms. It was about 7th grade. And how do you multiply them? FOIL. But now there's like distributive law. Just go. 8th grade. Every time you multiply elements in R1 times R2, that's the multiplication in the ring capital R. So this is called the polynomial ring over R. Okay? You can add 2 variables, polynomial ring. You can also do this. Etc. Just another way of creating more rings from old rings. And the more ways you have of that, the bigger your source of examples will get. The more places you'll be able to test the validity of a statement. For example, a statement that might occur in a quiz. Is this true about every ring? Well, let me test my creativity of examples. Well, I just showed you 2 ways of vastly expanding your source of examples. Okay, great. There are other ways. There will be a way soon, maybe next week, called taking a quotient of a ring by a particular kind of subset called an ideal. Just like groups and quotient groups, there's going to be a similar situation with rings. Okay, moving on. Let me show you a simple theorem. Just for fun. Let me show you a simple theorem. Just so that we're not only doing definitions. All right, here's a fun little theorem exercise. Okay. If R is a finite integral domain, just parenthetical, and if R is not the zero ring, the trivial ring. Okay? Let's forget that. If R is a finite integral domain, then R is a field. Every non-zero element has a reciprocal, has a number element that when you multiply, you get 1, the 1 element. All right. Good. Let's see this proof. Here's one proof. One proof. All right. Pick any element which is non-zero. Right? We need to show that there is an element B such that A times B equals 1. That's what it means to be a field, folks. Every non-zero element has a reciprocal, has another element. When you multiply, you get 1. Okay. So how do you do this? Consider the multiplication by A map. Which sends any element to A times R. Okay. Now, by the definition of integral domain, multiplication by A is injective. And now we have a great situation. Since both domain and target codomain of mult A are two sets of the same size, two finite sets. An injective map between two finite sets of the same size must also be surjective or bijective. Okay, this is a little trick if you haven't seen this class. This is a trick. What just came out here? Just a small trick. You're collecting tricks of the trade. Finite sets, two finite sets same size. If you want to show something is... If you want to show a map is surjective, you can show injective instead. All right. So that means, what's the utility of this? Therefore, there exists an element B in the domain such that you see, we know it's a surjective map, so I look at the element 1 in the target and I ask, well, there must be an element in the domain which maps to it. So that's what I wrote out. There's some element B such that this is one. And so now you're done. QED. All right, that's one way of proving it. You want to see another cool way to prove it? Another way. Read the book. The book has a different way. It's a nice way. It's another nice way. Has another nice idea. Trick. Okay? What is the other word for surjective? Onto. Great question. Onto. And this is 1-to-1. Okay? But use surjective. You'll and wear a bow tie. You'll rise. You'll go up in the world. Okay. Yeah. Okay. Great. So, what a beautiful theorem. All right. Great. I just want to mention a couple things about fields. Some believable things about fields. One thing. Okay. If F is a field and a non-zero element, then there is a unique element. I.e., there exists a unique B such that A times B equals 1 and B times A. Everything's commutative when we talk about integral domains and fields. All right, so there's a unique multiplicative inverse. I don't want to do this proof. Look at group theory proof. Same proof. Okay, awesome. So, and another thing is, so given this, we write A inverse for multiplicative inverse of A. The multiplicative inverse All right. Another thing, class. Another thing that I didn't say explicitly. Fields are automatically integral domains. And that's because if a times b equals 0 and a is not equal to 0, I'm looking for zero divisors. Oh, if some non-zero number times b is non-zero element times b is 0 and a is non-zero, multiply both sides by a inverse. Remember, anything times 0 is 0. Super general fact for all rings. Okay, so this is b equals 0. So if a times b equals 0, and you know a is not 0, then b has to be 0. It's not it's not like 2 times 3 is 0. Get it? Yeah. Okay. So fields are once you have that ability to divide, it's great. You got a lot of good stuff coming your way. Fields. Here's how you think of fields. The main utility of fields. Division is a thing. This is where in the DNA of mathematics, which is what we're kind of trying to get at here. We're trying to get at the sort of source code that if something was true in a wide setting, it's good to know that. We're trying to understand the broad strokes of algebra. Where does the concept of division really come in? In the definition of a field. So you get fractions, 1/2, 3/7, 2/8. All of those all the fractions form a field, and we're trying to generalize that ability to do reciprocals, and that's where the notion of fields sits. Okay, great. Anyway, let's go on to part 2 of my awesomely scheduled programming. Another definition: the characteristic of a ring. All right, let's talk about that. It's just a definition. It's an important definition. So let's learn it carefully. All right. So here's the setting. So this is the characteristic. Oh, awesome, Steven. Awesome. Yeah, I know the Ross program. That's good. Awesome. Characteristic of a ring. Okay, here's the experiment you do. You do the following experiment. Did I say experiment?
Yes, science.
Okay. Take the element 1. Add it with itself. Add it again. And just keep adding 1 with itself. Okay, this is the experiment. Brilliant. It's deep. It's literally just, you just take the one element that you know is not, probably not the 0 element. If it is, then you're looking at the dumbest ring possible. But okay, take the next ring. Just start playing. Oh, just keep adding itself with itself. Okay? There are 2 outcomes. 2 outcomes. Either at a finite stage, you get to 0, adds to 0 at some smallest finite number n, or you never hit 0. Okay, there are two. Obviously, there are those. Those are the two situations. All right. So now I'm going to show you. I'm going to tell you a definition from this. Definition. The characteristic of a ring R. Oh, 1729. Awesome. The characteristic of a ring R is the number n in case number 1, or we just declare the characteristic to be 0 if we're in case number 2. Examples right away. Definitions. Do not think that just because you're in the definition zone that you can just sit back and be like, well, I don't have a watch. Okay. Well, I mean, let's just wait for the theorems to come in, folks. Wrong. You will just be drowning in incompetence if you do that. When you're in definition zone, it's you need to, in a sense, be highly engaged, thinking about all the different creative ways of creating rings and testing. Otherwise, you'll drown. Sometimes in future, if any of you become mathematicians, sometimes it takes like 8 months to fully grasp a single definition. No joke. Don't devalue definition. Okay, but this one's easy. Look, examples. The characteristic of Z mod 8Z is, drumroll, suspense, 8. Okay, here's another example. The characteristic of Z mod 10Z, adjoin 2 variables. Polynomials with Z mod 10Z coefficients, 2 variables, x's and y's. Characteristic of that is 8. Because the identity element, the one element in this ring, is just the constant polynomial. 1 times x to the 0th power. So, what's the smallest number of times you add this to get... Oh, 10! 10! 10! 10! Okay, the point is, folks, I just wanted to point out that the one element in the polynomial ring is 1. The polynomial that has only the constant term, 1. Think about it. Multiply. Okay. All right. Example. Z has characteristic 0. Q. Characteristic 0. R. C. Awesome. So, Now, what was I supposed to tell you about characteristics? Part 3. Third part. You're just knocking down this lecture. Awesome. I can't believe people came today, given the world events. Okay. Oh yeah, everybody, we have emotes now. I don't know if you have to have Frankerface Z browser source. No, browser extension enabled. You get BMPOG. All right. Good. All right, let's go. So, what was I going to tell you? Right. Here's an awesome fact. Okay, awesome. Super easy fact. If R is an integral domain, then the characteristic of R, oh yeah, we just write char or characteristic. Then characteristic of R is either 0 or a prime. There's only 2 options, folks. That's it. 2 options. Okay, let's see why. Proof. This proof is like one of those, okay, put 0 aside. Let's assume it's not characteristic 0. We must then show that the characteristic is a prime number. We must show that characteristic R is a prime number. Let n be the characteristic. And suppose it's composite. Well, no. Suppose n equals a times b. Or a times b, yeah. A times b for 2 integers. Okay? All right. Then if you write 1 n times, okay, you can cluster them into A B's. And then you can factor it out. Factor out the sum of A's. Now, n was the smallest number where you add ones and you get to 0. So A and B, if they're smaller, we guarantee that these 2 quantities are not 0. These 2 elements are not 0. All right? And what do we know? We know that this is 0 because we're looking at the characteristic. Okay? And so, if both A and B are smaller than n, R would have 0 divisors. Namely, these two elements would be 0 divisors. Bad news if you're in an integral domain. So, A equals 1 or B equals 1. In other words, it's impossible to factor n in any way other than 1 times n. Okay? Easy. Very simple. Very simple principle. So integral domains only have prime characteristic, or they have 0 characteristic, where everything makes more sense. It makes more sense to a human being that when you add up 1 with itself, you never get to 0. Characteristic 0 kind of closer to our life experience. Characteristic prime, a little bit more mysterious. And we'll learn about the true mystery, the differences between these situations. Okay? So I want to emphasize that as a huge theme. Huge breaking fork. Huge fork. In the study of rings and fields, there's a huge fork that happens. There's the characteristic 0 path, and there's the characteristic finite characteristic. Okay. Oh, yeah. Terrible notation. Finite characteristic is the phrase used for like characteristic not 0. I didn't do this. Okay. Finite characteristic. Interesting characteristic. And folks, we will be mostly interested in fields moving forward, especially next semester in Galois theory. So you'll see the word characteristic P. Okay? You'll see this all over mathematics in the field of number theory. Characteristic P. Oh, I proved this and this, but not in characteristic P. I still have to work on that case. Or, I was only able to do this in characteristic P. The characteristic 0 case has a separate argument. You will see this fork throughout subjects that have fields in them and rings. The characteristic 0 and characteristic P divide. I want to introduce that up front to you as part of the sort of a way to classify your massive list of examples that you're developing over time. Okay? Good. If you didn't understand this, don't worry. Math makes way more sense here. Okay? And over here, math is a bit strange, but wonderful. And believe it or not, extremely useful. Even if your original intention was to understand a characteristic 0 situation. Okay? This is the general story of number theory. Okay, awesome. So, we know what the characteristic of a field is, of anything. It's the total number of times you add 1 to get 0. Okay, the smallest quantity. Okay, one last thing about characteristic. Simple thing. If R has characteristic n, then for any element. If you add r n times, which by the way, we write shorthand simply as n times r. Okay, that's a 2r. What we mean is r plus r. Let's do that. Okay, that's the notation. This thing is 0. It's true for all elements. Once it's true for one, the element 1, it's true for all of them. Because r plus r plus r is actually just this multiplication. Use your distributive law. And this is 0 times r. Okay? So everything, you add it with itself n times, you get 0. That's so the characteristic rules every element. Not once it rules one, it rules every element. Okay, awesome. So, finally, that's a definition. Go through your list of examples and classify them as finite characteristic and characteristic 0. Now, I had one last thing I needed to tell you about today. Right. Possibly the most important definition of the day. Ring homomorphisms. Is there a list of these emotes? Not to be confused with eminent domain, which is when the state takes away your field. Okay, ring homomorphisms. Every single subject, class, every subject you ever learned from here on out, whether you're my student, anyone else's student, in every subject, look for the objects, rings, groups, sets, are vector spaces. This is linear algebra. Look for the objects, and then right away, then immediately look for the relationships. The relationships will be encoded by a concept which tries to relate two of the objects. The structure in two of the objects. It tries to relate the structures. And that's when we get the concept of a ring homomorphism. This is the tool by which you can start expressing the way two rings are related to each other. Okay, suppose R and S are two rings. Definition. A ring homomorphism from R to S is a function. And I'll say it colloquially. Slang definition first, which respects the ring structures. Let me now write that out. Let me write it all out. B is, first of all, a group homomorphism between the two abelian groups. Focus on plus. Only plus is a group structure, folks. The group homomorphism. It respects addition, right? So phi of A plus B equals phi of A plus phi of B. Okay? 2. Phi of 1 is 1. And then it respects multiplication. Okay? This is the device, a ring homomorphism, which will help us, which gives us a notion of relationships between various rings. Okay? And just like before, ring isomorphism has the obvious. Okay, once you have this thing, then ring isomorphism equals ring homomorphism plus bijective, etc. so on. Okay? But that's, I'm showing you this device early. I'm not waiting until chapter 15 because it should come early. It's the way we start relating two rings with each other. All right? So starting next class, I'll just play around with, I'll show you some homomorphisms. I'll look at some rings. We'll look at some characteristics. And then we'll arrive finally at the concept of an ideal. Again, another definition. All right? Setting us up for quotient rings next week. Awesome. And I'll do some more motivation. So next time, plus more motivation. Because we're lacking in motivation right now. I know that. I did a bad job. So I got to add motivation and then key concept added in, an ideal of a ring. Awesome. Now, I look at this degenerate chat and we start winding down. Credits. Let's get our dopamine while it's hot. Credits. Bro. Teacher's pet. And teacher's pet and propping up this place with the cash. All right, bro, teacher's pet. All right. Hey, can you keep it down, BMP? I'm taking an exam. What? Hangs mate in one. Contributed terrible pun. Okay, algebraically challenged. Moderator. Yeah. Actually, yeah. Let me just cross that out. That was bad. All right. And oh, there are some new people. There's a new person here. Steven. Ooh. Can't read that. Ew. Okay. Cross that name off. Oh, you meant Crow? Okay, fine. I'll cross anyone else. Okay. I'll cross both of them off. Okay, good. All right. Hey, Steven, how's it going? Who else? RDL was here. RDL and Sloth, I saw you. I'm sure the other students were here too. Okay, math sucks, boo. Okay, you're not gonna make it in the thing. That's good. And yeah. Hi, what do you think about triple asterisks? All I see is triple asterisks, my friend. Okay. All right. RDL Sloth. Maintainers of the tricks. They maintain, along with the other students, they maintain the secret bag of tricks. But now we have ring theoretic tricks. All right. Okay. I bet they were trying to rickroll me. I just guarantee it. That was a rickroll attempt. Blocked. Oh no, Sloth, you're having internet problems. Ah, that sucks. That sucks. Alright, so this is the credits. Remember, we always think we thank the originators of the concept of rings and fields for giving us this playground to investigate. Okay, here we go. You know, Hang's mate in one. Changed my mind. Okay, awesome. Let's get out of here. I gotta learn ratio test. Oh, you got your dopamine back? Okay, good. That hopefully you'll have a better day now. Hang's mate in one. Okay, ratio test. What is that? Okay, that's what I gotta learn quickly before the next class. I gotta go do that. And thanks for all the people who followed. You're a bunch of weirdos. With that, outro.